problem 2.5, a model for a standard 2D cell flashing light is shown in this picture. Find the power dissipated in the lamp. If we look at this lamp is basically represented by a resistor with a resistance of 1 ohm, right? And the voltage applied on this lamp. So we have about one battery and one battery, these two batteries in series. So this is a positive end, right? So the other side is the negative side. Oops. So this side will be negative side. So it means the voltage on this end is higher than this end by 1.5 volts. The second battery is the same. So it means this end is higher than this end by 1.5, and at the same time, because these two are connected together, so this node is higher than this node by 1.5. So it means that in total, this node will be higher than this node. This node is connected to wire. This is by 3 volts. So it basically tells us that the voltage on this lamp is 3 volts. So the voltage on this is 3 volts. And the resistance of this lamp, that is 1 ohm. So from Ohm's law, we know that V that is equal to R times the current I, right? And from the way to calculate the power, from the power calculation, we also know that the power can be calculated by using the voltage times the current. By combining the two, we can find the power calculation for resistors. So if we replace the current I by using the Ohm's law, the current I that is equal to V over R, and it becomes V squared over R, right? So that will give us a 3 squared over 1, so that will be 9 watts. So 2.11, find the current I1 in the circuit. So whenever we are looking for a current, at least from what we have learned from this chapter, we know that when you want to find a current, you probably think about KCL, because KCL tells us the relationship between the currents connected through one node, right? So the KCL tells us that the algebraic summation of all the current goes into the node is equal to 0. That is equivalent to say the algebraic summation of the current leaving the node is equal to 0. You can also write it in the form of the summation of all the current goes into the node is equal to the summation of the current leaving the node. So there are 3 different ways to write this KCL equation. So let's look at the problem. We are looking for I1. I1 is over here. And what's given in the problem is that this branch is given, this current in this branch is given, this current is given. So if you are not very familiar with the new technique that we learned before, we mentioned in the class, that you can probably do it slowly, say like this current is connected with this node, or you can look at it from here. Either way is fine. If you look at it from this node, I don't know the current in this branch. I know the current in this branch, so I need to further find the current in this branch. If you want to find the current in this branch, you probably look at this node. Okay, the problem is solved. You can solve this current first, then solve current I1. So this is the first method to solve this problem.
Professor, question?
Yes.
Could you call those 2 nodes with the resistor a super node so that you could just turn it into the 4 currents that are either leaving or entering that super node?
Yes, that's the second method that I want to mention. So
Oh,
the second method, you can define part of a circuit as a supernode. You can assume that it is a part of any part of a circuit to be one node. If I define a node over here like that, so say I'm going to define my node A to be that. So define part of the circuit as a node A. By looking at this node, we have one branch, have a current I1 leaving the node. That's something we are looking for. And this is branch, the current in this branch is known, the current in this branch is known, the current in this branch is known. So it looks like all these 4 different branches, 1, 2, 3, 4, only have one unknown. So we can solve the problem like that, right? So we'll say apply KCL to node A. So we will use the current leaving the node as a positive, so that I will have a positive current I1. And this is 2 milliamp minus 2 milliamp because it goes in, right? We use leaving the node as a positive. So this is goes in minus 12. So this branch leaving plus 4, that is equal to 0. So we'll be able to find I1. I1 is equal to, this is 10 milliamp, right? Remember, we are using milliamp. So let's look at problem 2.14. In this problem, we're going to find Ix in the circuit. So Ix is over here. And different from all the previous examples, we have a dependent source. So this source is a current source because it has this arrow there tell us like what is the direction of the current. At the same time, this current depends on another current, Ix. This current is always 5 times of Ix. So we call it a current-dependent current source. So we're going to find Ix. By looking at Ix is connected to this node. Oh, by the way, this is one node. So although we have 2 dots over here, this is one node because there's no element in between, right? So we have connected to this node, and at the same time, there's another current connected to this node, a third current connected to this node, and the fourth current connected to this node. And by looking at this node, we only have one node, which is Ix. That is super nice, right? So we'll say, we'll define this node as my node A. Then we'll say apply KCL to node A. We'll be able to write the equation, the KCL equation. And we'll use the current leaving the node as a positive. If we do that, it will be Ix. This is a positive 10 because it's leaving, right? And over here is a minus 5 Ix, and this is a minus 2. That is equal to 0. And then we will be able to solve for Ix. So we have a 4Ix that is equal to 8, so Ix that is equal to 2 milliamp. So in this problem, we're going to find a VAD and a VCE in the circuit. So these are the nodes A, B, C, D, E. VAD, so it means A with respect to D. So this is the current of VAD. And plus sign and the minus on the right hand side. To find a voltage in the circuit, we will need to use KVL. If I want to find this voltage right here, definitely my loop should include this voltage. So we'll call this loop 1. KVL to loop 1. We'll write the equation. We count the voltage drop by following the loop that I defined, right? So the first drop from A to D, that is something we're looking for, VAD. And from D to E, that is -1, right? Because this is from the lower to the higher. So you can also see it as like I'm gonna, by using the sign that I first seen. So I see a negative sign, so that it becomes -1. Then over here I see negative sign, it means that it's a negative for Vx, right? We counted all the elements in the loop, so that adds up to 0. So Vx that is given as 2 volts. So we'll be able to find a VAD that is equal to 1 plus 8, so that is 9 volts. Right? So the second part of the problem, to find a VCE. C is here and the node E is over there. So that is my VCE. So we need to find another loop to do that. I'm going to use this loop. So this will be my second loop. So I call it a loop 2. So apply KVL to loop 2. So the first voltage drop is VCE. The second voltage drop is 1 volt plus 1 volt. The third voltage drop is from here to there. That is minus 12. That is equal to 0. So we can find a VCE. So VCE, that is 11 volts, right? So that's how we solve this problem. Let's call this method 1 that we use KVL. The second method, I'm going to use the definition to find a VAD. We know that the definition of VAD is the voltage difference between A and D. We can find that voltage difference by following any path. There's one path over here, there's another path down there. So I can find a VAD by using the definition that is voltage drop from A to D. So I can find it from here. VAD is equal to the first voltage drop from A to B, which is negative 1, and second voltage drop from B to C, that is minus 2. The third voltage drop from C to D, that is plus 12. So you can find it that way. That is 9 volts. You can do the same thing to find the voltage VCE, right? So the VCE means the voltage drop from node C to node E. You can follow this branch, you can follow the other branch, either way is fine. Let's see if we follow this branch from C to E. So I have first voltage drop of 12, the second voltage drop, that is minus 1, that'll give you 11, right? You can also do it the other way. I'm going to find a VCE from here to here, the voltage drop. So the first voltage drop from here to there, that is 2 volts. The next drop is 1 volt. The next drop is 4 times 2 volts. So you can also get like 11 volts from that. So either way is fine.